Hey everyone, welcome back to MLWorks. In this video, we'll be learning how to write a CUDA program for matrix addition. In the previous video, we started with CUDA programming and we implemented parallel vector addition, and we learned a few keywords for CUDA programming, and one of them was global qualifier, which is how you write a kernel function. And then we also learned how to move data from CPU to GPU and how to allocate memory inside CUDA, and how to move data back from GPU to CPU. So in this video, the main idea is to understand how does a data structure like a matrix is mapped to threads in grid block. So that's the key idea. And we also, while we are doing that, we'll also understand how to use the 2D properties of the CUDA grid block to determine the row and column indices for the matrix. So when I say that, we want to map each of these elements inside the matrix, which is A11 plus B11, where you have our result, how to get it mapped to specific thread. So we want to create 100 threads. If you have 10 cross 10 matrix, if you have 100 elements right inside a matrix, you want to generate 100 threads, and each of those threads will have their own index. And since it is 2D matrix, so you will have index I comma j, and you have to map your threads to matrices. So we'll understand all those, and we'll also understand why we are trying to save the array in the row major order, where you will be storing matrices, multi-dimensional matrices like this, into one row after another. Like as mentioned here, 1 2 3 4 represents the first row, and then 5 6 7 8 represents the second row, and so on. So why we are storing that also, we'll understand that aspect. So with this, let us get started with matrix addition. So 2 cross 2 matrix, how you add is, consider right here you have this A matrix and B matrix. You will be performing element wise addition. So A11 gets added with B11 and get the final result. Similarly, other elements are added. So now let's go and implement matrix addition, and in day 2 I'll be writing this file matrix underscore addition dot cu. Cu represents the CUDA file, and it is an extension for the CUDA program. Now first step is to include the IO library, which is IO stream, and then for performing the math operation we include cmath, and then we'll be defining the dimension of the matrix, which is const int n is equal to 10. The matrix will be 10 cross 10. So this is for A, B, C. You will have 10 cross 10, 10 cross 10, and 10 cross 10. There will be 300 elements totally. So now let us define the kernel function, which will use 2D grid and 2D block. So first is the global qualifier, followed by the return type, that is generic in this one, and function name, which is matrix addition. And this will take in 3 matrix A, B and C and the size of it. So it will be int floating point variable, int floating point variable, int and floating point variable, followed by int size, which is the size of your matrix. Now first thing, right, this is defining the matrix dimension. So let me write a comment here. So matrix dimension. So now kernel function, and it uses 2D grid and 2D block, not 3D block, 2D block. And so since it uses 2D grid and 2D block, so whenever a function is called, this kernel function is called, it will generate many threads, and each threads will have their own unique index. So in this case it will be I comma j, because we have 2D block or 2D grid. So similar to this, right, if you look at this image here, we have inside a grid we have blocks, and inside each block we'll have group of threads. Now that thread has an index. For this scenario you will see there is x, y and z, and in our case it will be x comma y. So we want to declare this index now. So first int I is equal to block index dot x into block dim.x plus thread index.x. So this represents the column index, and let me copy this and paste it here and change this to y. This will represent the row index of the matrix. So just to go back here, so this index that we are seeing, okay, this is part of your x block index dot x. This represents by column index. It represents the column index of the matrix, and that y what we have storing, right, idx dot y, it represents the row index. Now here if I want to go a little more depth here, right, so column index, the block idx represents the index of the block in the grid, and followed by I have dimension, which is the number of threads in the block, and plus I have index of the current thread in a block. So you will notice this everywhere. So first is index of the block, this index, and then we have inside this index number of threads that we want to have, which is block dim.x, and thread index is the location of the specific thread. Okay, so this is done for both x and y to exactly pinpoint each thread with their corresponding global unique index. Okay, now let me write a boundary condition here first. I less than n and not n, it is size, then j less than size. So as I said, I and j are your thread index. Now since we have only 100 elements, only 100 elements are present in a 10 cross n 10 cross 10 matrix, but when you are calling this function, there will be more than 100 threads. So what you want to do is you want to ensure that your thread index, which is I comma j, doesn't exceed your size of this matrix, because if you have I comma j which is greater than 100, right, what will happen is it will try to access a memory and it will try to perform some calculation where nothing is present. So it will throw an out of bound memory access for a thread. So that's why we have to perform this boundary check, and then we have to perform our row major order indexing, so which is done with the help of int I into size plus j semicolon. So this will be the way how our index are calculated. So all these elements is turned into this type of index, and this is calculated with the help of this specific formula. Okay, now we can go ahead and add our elements. For a of index plus b of index semicolon. So we are almost done with the kernel function. Now what we'll do is we'll be writing our main function where we'll call this specific kernel function. So main function, and first thing is return type and main, then followed by declaration of the matrix size, which is const int matrix underscore matrix size is equal to n into size of integer. This is the total size of your matrix in terms of bytes. And then what we do is we declare the variables in our CPU such that we can move the data from CPU to GPU. So first let's declare the variables, which is int pointer variable h underscore a into not into is equal to new, and int the size would be n into n, which is 100, 100 block of memory is assigned for HA. Similarly, we want to do that for HB and HC. Now we want to fill this matrix with some value. So for I integer I is equal to 0, semicolon, I less than n into n, semicolon, I, that is plus I. And here we want to add some variables, not some, put some values into the variables. So here I'll be putting as 1.1 semicolon, and similarly for for C I'll be setting it as 0 for now, because after addition it has to give some value, which is 3 for C array. So now we have filled our array as well. Okay, now what we have to do is now we have to declare the variables which will be used inside our CUDA or GPU. So which is done with the help of int into d underscore a, d underscore b, and d underscore c. Now we have declared the variables. Now we want to assign memory to these variables, as we have done here, right? How we have assigned memory here. Similarly, we want to assign for this device also, device variables. So which will be done with the help of cudaMalloc, and it will be pointing to the specific variable with the help of void **da ampersand da, and which will be matrix size. This is the amount of memory we want to assign. Now similarly it has to be done for db, dn, dc. We have for db, dc. Now this is done. Now what we have to do is, we have memory assigned in our device. We have elements present in our CPU. Now we want to move the data from CPU to the specific variables which are assigned in device. So which is done with the help of cudaMemcpy, and we'll be moving it to DA from HA, and the memory size is matrix size, and the operation is from host to device. So cudaMemcpy from host, not from host, host to device, and semicolon, and have to do the same for B as well. B array also has to be passed. So now we have moved our data to these variables. Now we have to perform the operation in parallel. So we have to make the call to the kernel function. So first let us define the configuration for the kernel function with the help of dim3 data type, and variable name is block dim. This will represent the number of threads inside your block, which is 32 cross 16. And then dim3 and grid dim, which represents the block size, which will be divided by n divided by this block dim. Okay, so what we'll do is, first I'll be requiring an integer, so I'll pass the typecasting first. Then I want to perform ceiling function, and first I have to typecast to float here whatever the value that comes up. First I'll be sending here n divided by block dim, not dim, it will be idx dot x. So this is what we have to do again for this one. Instead of yx we have y. So this will basically perform only one thing, which is 10 divided by 32 comma 10 divided by 16. So this represents the y, block index y, block index x. So this will give you some value called 1 comma 1, since we are performing ceiling function, right? So it will get you the 1. So once this is done, now what we have to do is, we have to make a let me add a semicolon here first. We have to make a call to the kernel function with this configuration. So matrix addition, and followed by grid dimension, followed by block dimension. Close this and pass the parameters d underscore a, d underscore b, d underscore c, and the number of elements. which is n cross n, which is the matrix dimension, which is n, and this will perform the operation matrix addition, and you will get your results. And after that, what you have to do is, since we want to run this, we want to also ensure that all the operations are done, then only we move back the results. So what we do is CUDA device synchronization, and this will ensure that all the operations are done here, then only you can move on back the results from your GPU to CPU. So for that, what you have to do is just copy this line and paste it here, and instead of host to device, now you have to move it to device to host, and it will be, instead of D, it will be h_c from D_c, because finally our results will be stored in DC. And so since we are done with getting our results back, what we can do is we can free the memory that is occupied by device and even by the CPU. First we'll remove for CUDA free, so this will remove the memories occupied by these variables, and then D_b semicolon and CUDA and free D_c. So we have freed the memory in the device. Now what we can do is, since we have copied the result, now we can print the results. Let us see how we can view the results. So first is for I int I is equal to 0 semicolon I less than n into n semicolon I plus I, and then print the elements, which is C. So standard out, C out, and this will give me h_c, and I'll be giving the index here, and I'll be writing one comma and space in between each element. So that's done. The return type is 0, because it is an integer return type we have provided for the main function. So we are done with this, and now what we'll do is we'll be running this by compiling the code. So it is day 2, and here we will be using NVCC, which is the compiler for compiling the CUDA program. So matrix underscore addition, and then output would be stored in mat_add. So let us see if it works. So warning, what is the warning here? In the main function, device built-in variable block index. So I think I might have screwed this up a bit. So here I think we have to, instead of the index, right, we don't have to pass the index, we have to pass the dimension, because that is where you have this 32 and 16 stored. So it will be dimension, not index. So let me clean this up. Again, run this NVCC matrix addition. So it got executed. Now let us see the results. So this is stored in mat_add. So I'll just, so yep, we have our matrix, which is totally containing all the 3s. It is coming up after we have added HA and HB, and we got finally HC here, and instead of 0, it contains all the 3s after the matrix addition. So the most important part in this program is to understand why we are setting this row major matrix like block of memory, right? Not as a 2D array, why we are using row major order. So what happens is, when you are dynamically allocating memory in standard C++, so for every row a block of memory is assigned. It's not like all the 3 rows are assigned one after another. It will be assigned as a block of memory for every row. So there will be 3 different blocks of memory assigned across your memory space. So when you want to copy your data from CPU to GPU, you have to iteratively pass this block of memory. it is not already present in continuous block, it is in separate location. You have to pass them iteratively. So which makes the whole performance slow and little tedious also. So that's why what we do is we store this multi-dimensional matrix as row major order as mentioned here, and then we send the whole block of memory or whole block of array to the CUDA GPU and perform the operation. So that is the main point. And also the important point is you have to understand how we are setting this index for your matrix inside your GPU. So this is also important. So with this, I'll be concluding this video. Thank you for watching.